Okay, solutions. Solutions. Solution? Okay, so solutions. What is a solution?
Solution is like a mixing chemical.
It's definitely liquid. Yep. It goes mixy in a liquid. It goes mixy in a splashy boy.
Exactly.
What?
Are we finally going to do Kepler and SpaceX, or do we all not soon stop?
Kerbal?
Or,
Yeah, we're gonna do Kerbal.
Okay. Space plane stuff?
No. Okay, maybe. Wait, what? A pet snail? Oh, guys. You have any idea? Look, guys.
He's so cute.
Oh, come on. I need a human for scale. That one's pretty good.
Oh my gosh, they're so cute.
They're fun. Well, that one's all pale. Yeah, I mean they're pretty good size, right? Can you eat them? Forbidden. Okay. Anyway, giant African land snails. Yeah, they're pretty cool. I saw a picture of a lady holding one. It was like a cat. Like it was most of her forearm and her hand. Okay, anyway, so solution is stuff in a liquid, okay? And oftentimes in chemistry, we talk about an aqueous solution. What is an aqueous solution? Any ideas? What does aqueous mean?
2 out of your top 5 videos are me.
Means watery. Yes, water. It's stuff in water, which is essentially everything that you interact with liquid-wise on a daily basis. Okay? Anything that you drink is an aqueous solution. Okay? So you drink milk in the morning, or you drink almond milk or soy milk. That is stuff in water. Okay? You drink Gatorade, you drink Coca-Cola. For those of you who have a death wish, you drink Monster. Yes, JJ, that's exactly what I was talking about. Okay? That is a bunch of stuff in solution with water. Okay? Water with stuff in it. Very, very technical definitions, okay? There are non-aqueous solutions, but when we talk about a solution in chemistry, it is almost always water-based, okay? It is almost always water-based. So why are solutions important in chemistry? Yeah, that's not how you do that. No. Solutions in chemistry. Listen, okay, I didn't have nitro type when I was in school, okay? I actually, paid attention in classes and yeah. Okay, so solutions in chemistry. Why are solutions important in chemistry? Why is it that we care about chemicals being mixed together in a liquid state?
Because sometimes they make explosions.
Because sometimes they make explosions, that's yes. But let's think about chemical reactions. Okay, chemical reactions occur best when there is high surface area and high concentration, right? A solution is the best of both worlds. Solids are high concentration, but they have very little surface area and they can't, the molecules can't move around. In solution, molecules are free to move. Molecules to move, free to move, cuddle, link up, okay, and react. In solids, they're frozen in place, right? So like if you try and react, when you burn wood, wood burns slowly, right? Gasoline does not. Why is that? Because wood, even though wood and gasoline actually have very similar chemical reactions when you light them on fire, wood being a solid only has a certain amount of surface area available for the oxygen to make contact. With gasoline, you have a liquid. That liquid very quickly evaporates and you burn it very, very quickly, okay? Speaking of, my dad, like 10 days ago, we were on our way to New Mexico. New Mexico, Los Alamos, New Mexico. Emma, are you making fun of me? Emma's making fun of the fact that I mentioned that like 5 times.
Everyone's taking it seriously for the past like 2 weeks, and I'm like, dang, never mind.
Anyway, so Emma's making fun of me. So I was at my parents' house, and we were having some good old hot dogs over the fire, and my dad was like, yeah, this fire isn't happening fast enough. Comes out of the shed with a gas can. Yes. And just pours gasoline on an open flame. And I'm sitting right there with a baby in my hand. I'm like, Dad, this is not a good idea. Anyway, so on our way back, I stop at my parents' house again, and my dad explains to my nephews, hey, remember that thing that I did with the gasoline on the fire? That was not a smart idea. Anyway, so solutions are important, all right, in chemistry because they allow chemicals to react in a high concentration and a high surface area, okay? Concentration and high surface area. Okay. Hey, I think that I spelled everything right there. It's pretty good. Can we just take a moment to have a moment of silence for the people that had to type on typewriters and there was no such thing as backspace or delete? You used to want a typewriter and then you realized, holy crap, that is an ancient piece of technology that is completely useless. They're hard to find and they're expensive and they're completely useless. They're so popular because of a bunch of freaking millennial hipster people are like, oh, I want to write my novel about avocado toast on a typewriter. I've got fan fiction about avocado toast. All right. I enjoy avocado toast as much as the other millennials, okay? Yeah. Am I a millennial? Yeah. Yeah. What? You think I'm too old to be a millennial?
Yeah.
Get off my back, guys. I'm 1 generation ahead of you. 1.
stuck for like.
No. The oldest millennials are like, no. The oldest millennials right now are like 39.
Yeah.
Hannah, watch it. Okay. So concentration is high, surface area is high. This allows for reactions to occur. Allows reactions to occur, whatever. Quickly, or I don't know what, I'm not going to finish that sentence. Okay. So you get the gist, all right? Solutions are important because chemicals are able to react because they move around each other. Molecules are able to link up and cuddle and find their soulmates or whatever.
You're just gonna do today.
Okay, so aqueous solutions, Y is what? Oh, that I don't have a text box. Got to make a text box first. Meh.
I think you said TikTok. Yeah, I also like TikTok. Oh, I reference it real quick.
Oh, I have a TikTok. All right. Water.
Yeah.
Why is it such a good solvent? Okay, so what are solvents? Why is it a good solvent? So what is a solvent? Who could give me a definition of a solvent? Okay, solvent is liquid with stuff in it. Solute, S-O-L-U-T-E, is the stuff that's in the liquid. Got it? Whoa. Solute, S-O-L-U-T-E. Solute. Okay, so why is water such a good solvent? So water is considered the universal solvent because it is polar, okay? Polar, but just barely, just a little bit, okay? We've talked about polarity before. What does polarity mean in a molecule? What?
No. I was just saying, was it the periodic thing that
Ooh, that's electronegativity. That's a yes. That is important to remember. But polarity is different. The electromagnetic stuff is you're thinking along the right lines here. But polarity is when one side of a molecule is positively charged, right? And the other side of the molecule is negatively charged. It is a polar molecule, just like the Earth is polar, or a magnet is polar, okay? What happens is, I'm actually gonna get rid of that part. Time for some drawing. I know you're all excited. Oh, I'm excited. I'm so excited, it's freezing. Says Shelby. Okay, so a water molecule is a Mickey Mouse head. Okay, we have two hydrogens and an oxygen, right? The hydrogen, the side with the hydrogens on it is positive. The side with the negatives on it is the negatives. The side without the hydrogens, where the electrons want to hang out, is negative, positive, negative, okay? This is really important for dissolving polar molecules. So what happens if I put some salt in a cup of water? It dissolves, which means what? It makes a solution. It disappears, right? It just kind of goes away. It becomes one with the water, right? Did the salt, which is, remind me what the chemical formula for salt is?
it's two different things.
NaCl, two deadly things. Yeah. Sodium chloride. Okay. Sodium chloride, NaCl. When those two things, when you put the salt in the water, does the NaCl just disappear? Does the NaCl just go away? Just poofs out of existence? No, what it does is it dissolves into the water, becomes a saltwater solution. Right? It becomes a saltwater solution. So what happens is we have these water molecules, and we have I'm going to do the let's do red. The salt molecules in red here. So there's our chlorine, and here's our sodium. Okay. And when you pour in the sodium chloride into the water, it will be like this. It will be in a crystal where the sodium and these should be connected. Sorry. Okay. Sodium chloride, and we have a little one here and a big one here. Okay. They make a lattice like this, okay, where there's an attraction because this side, which is the chlorine side, is negatively charged. This is a another polar molecule. Positive, negative, okay, positive, negative, okay. So it makes a lattice. Like, essentially, if you were to build something out of a bunch of magnets, those magnets would all have a very specific orientation. They would want the positive side to be closest to another negative side, and so forth. Interesting, actually, salt crystals are perfect squares. So if you get just a tiny little salt crystal and look at it under a microscope, you'll see that it will be in very nice 90-degree angles. Okay? And that is satisfying. Okay, so what happens here is we have these water molecules. We'll do these in black again. The water molecules come over, and the negatively charged side that does not have the mouse ears is attracted to the side that is positively charged here, and it actually comes in and pulls this guy away, and they kind of go off and do their own thing. Okay? And then another one comes in like this. Okay? And we've got the negatively charged side here, positively charged side here, and it grabs it and pulls it away. Okay? So this is why salt dissolves in water, because the water molecules come in and they're like yoink. Okay? They're salt crystal home wreckers. Okay? They come in and steal molecules from the salt crystal. All right? So this is why polar molecules dissolve in water, all right? Okay. Now, non-polar, just as a side note, non-polar molecules do not dissolve in water. Who can think of something that does not dissolve in water? Cocoa powder. Hydrophobic, yes. Anything that is hydrophobic, which includes oil, okay? If I put some metal in a tub of water, is it gonna dissolve? It's like a chunk, just like a chunk of steel. Is it gonna do anything? No, okay? Because the metallic bonds between the steel don't care very much about the water molecules coming in and touching them, okay? It's the polar molecules of salts, okay? Things that are ionically bonded. If you have an ionically bonded molecule, It's generally polar, and that will mean that it is dissolvable in water. And how do we guess if an ionic bond is going to happen or not? When we look at two chemicals? Anybody? Two elements bonded together? All of you are going to be like, oh yeah. Remember, if you have something over here bonded with something over here, I mean, it's going to be ionically bonded, right? Because these guys really want those electrons. These guys really want to give them away. We get an ionic bond. So sodium chloride, NaCl, is obviously polar and is dissolvable in water. NaF, sodium fluoride, obviously polar, going to be dissolvable in water. Lithium bromide, okay? Anything that is an ionic bond is going to be dissolvable in water, okay?
Oh, yeah.
Oh yeah, yes, thanks, Leighton. Leighton following up on my prediction there. Okay, so questions about solutions, aqueous solutions or whatever. Sometimes you will see oftentimes you will see in a chemical equation, you'll have something like this where we want to combine two things. So oh my goodness, that was yikes. Okay, NaC, oh my gosh. It gets worse. NaCl plus, I don't know, something. In a chemical equation, you'll see this where they use an abbreviation. Yes, that is a Q.
I was actually going to ask.
Yes, this is an A and a very small-headed, long-tailed Q. It's an A and a snake. All right. So this means that it is in an aqueous solution. Okay? Aqueous solution. All right. So next time, well, this week, there is an assignment due. We're not going to start on it today. I'm going to teach you how to do the first part of it today. About solutions. Okay? It's called the solutions problem set. So the first part of it is you're going to be calculating percent by mass. Okay? This is really easy, so don't freak out just because I use the term calculating. Calculus? No. This is algebra-based chemistry. If you want to take calculus-based chemistry, you need to go to college. Lame. Okay. So if we, for instance, let's say we have 4.6 grams of, I don't know, cesium, which is super nasty. Cesium chloride. Chloride. Okay, and 55 grams of water. Okay. How would I calculate the percent by mass of the solution, or sorry, of the solute? So we are calculating percent by mass of the solute. Remember that the solute is the thing that's in the liquid. Okay? It's the thing that is dissolved in the liquid. Your batteries are low. Okay, thanks. So this is pretty easy. All we have to do is divide 4.6 by 55. Okay?
Just like normal.
Just like normal. Okay? It's just like 4.6 divided by 55, which gives us, well, that's a plus, which gives us 0.0836 repeating. Okay? So what is the percent of this solution that is cesium chloride? What is the percentage of the solution that is cesium chloride? So 0.0836 is already a percentage, but not of 100, but of 1. So we need to multiply this by 100, or just move the decimal by 2 places, which gives us 8.36%. See how that works? Yes, Mr. Croshaw. You're a great teacher, Mr. Croshaw. I'm really learning a lot. What, JJ? Oh, thanks. I need somebody to give me compliments, you know. Just over here fishing for compliments. All right. 8.36%. What? I'm fine. My wife last night was like, "You need to talk nicely to yourself." She said, "I don't like it when you talk to my Preston that way." That's the way that she said it. Yes, I knew it. I knew it. Were any of them originally made, was the original manuscript made on a typewriter? Because if so, we have achieved full hipster. What? An avocado toast fan fiction. It would probably get taken down off of YouTube immediately for inappropriate content, let's be honest. Okay, shush! Okay. 203, did you make another account to subscribe? You haven't been subscribed on your school? So you've subscribed with your 2 personal accounts, but not your school account. You seem to have done this. You seem to have done this backwards. Okay, shush.
I didn't really like a year ago.
Okay, so I don't remember what I was doing. Oh yes, another problem. Okay, again, percent by mass. We got to do this quickly because we only have 20 minutes left in class. Percent by mass. Okay. All right, 15 grams. Did I do 15 grams before? No, okay. In a solution that is, let's see here, 600 milliliters. Okay, what is the percentage by mass? Calculate it. Go, go, go.
15 divided by 600. I'm calculating. Hold on, don't say anything. I won't say. No, I'll cheat. Can't figure it out.
Okay, so what is 15 divided by 600?
9.025.
Okay.
And then you get 2, this is the 1, so it's 2.5.
2.5%. Well, that's an extra decimal point. All right. Okay, does that make sense to everybody?
Yeah.
Why did we do this? Well, because remember, in water, 600 milliliters is 600 grams, right? Milliliters to grams, nice and easy conversion.
Instead of what?
Instead of freaking, I don't know, ounces to stupid fluid ounces. Oh my gosh, the British imperial system sucks. It's so annoying, guys. It's so annoying. I'm telling you, there's a reason why students in the United States are behind in especially science. And it's because I have to teach you the unit system that we use. And no other place on earth has to teach you that. You already know it because no one uses idiot units in different countries.
Hey, I know 0 is freezing.
You know 0 is freezing in Celsius. That's good. I'm telling you guys, the easiest way to learn this stuff is change your thermometers at home to Celsius and on your phone, and change. This is totally gonna tick off your parents, but change your no, like anything that you measure distance for in kilometers. So.
Oh my God! Don't do that, dude. Don't.
Okay, so okay.
How many miles away are we? We are 12 kilometers.
Well, but let's be honest. Nobody in Utah measures distance with units of distance. Everyone measures distance in time for some reason.
We're about 40 people possible.
Because because people do not understand that time is not a measurement of distance.
Wow.
I live 45 minutes away. What? So in 45 minutes you'll just be at your house?
Yeah. Exactly.
I-50, yeah, exactly. Anyway, okay, so percent by mass, that's easy. All right, now, shush. Okay, now we need to calculate mass of solute. Mass of solute by percentage. Wait, mass of solute in, well, yeah, given percentage. Okay. All right. So let's try this. We have I don't know. Making up random numbers. 480 grams of solution, and it is 6.6. Do I do it? 6%. I don't know. Polar molecule. Let's do rubidium disulfide, S2. Okay. 480 grams, that is 6.66% rubidium disulfide. How much rubidium disulfide do we have in this solution? This one's pretty easy. All you have to do is 480 and multiply that by the corrected percentage. So again, we just have to move our decimal point over 2 spaces, but in the opposite direction, 0.0666, which gives us what?
I got this. Even though it's a sin, I got this. 30.4968.
0.968. What is the unit? Yes, 31.968 grams of rubidium disulfide. Okay. We see how that works? Pretty easy. Okay. 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 Now I need to teach you about molarity. So we've talked about it before, but let's be honest. How many of you actually remember what molarity means? You already taught us this, Mr. Croshaw. Well, how many of you remember? Not me. Molarity. What is molarity? Hold up. Control. Are you control Fing in your doc?
Which is the amount of moles in the solution.
Yeah.
And the concentration of the compound in the solution.
Okay.
That's
Good.
basically
Yeah. That is very good. Concentration of a compound. Of a solute in solution. Ooh, yeah. What was that?
Number of moles per molecule measured by mole per liter.
Okay, the unit, mole per liter. Okay. So mole per liter. Oftentimes, the way that this is shown is they will give you a solution. So they'll say sodium chloride, okay, NaCl solution. And then in italics, can I do italics in this? I don't know. Nope. They will give you like 0.7 M. 0.7 M. Okay. This will often be in italics. What does 0.7 M mean? Point 0.7 moles for every liter. Okay. Okay, 0.7 moles. So that means that for every liter, yeah. Okay. For every liter, there's 0.7 moles per liter of solution. So how many moles do we have if we have 250 milliliters? Milliliters to liters. What's the conversion between milliliters and liters?
It's not 1,000. It is 1,000. It's 1,000, guys.
1,000 milliliters in every liter.
So it's. I'm not sorry.
No, yes you are. Don't tell yourself that.
I can't do that. That's.
So how many moles are in a liter, or sorry, in 250 milliliters of this sample? So how are we going to do this? How are we going to do this? Well, first of all, I'm going to make some more space for us. Second of all, we need to determine how many. So we need to do 1,000 right? That 1,000 milliliters is equal to a liter, right? 1 liter. Okay, we have 250 milliliters, which is a quarter of that. No, just knowing off the top of our head, yes, we know that 250 is 1/4 of 1,000. But what if we do? What if it's like 425? We don't know that conversion, right?
It's a little less than half.
So what we need to do, it's a little less than half. What we need to do is we need to do 425 divided by 1,000. which gives us 0.425, okay, which is not all that surprising. But this is the way that we can do this, okay? And what do we do with that 0.425 to determine the number of moles in our sample? 425. We multiply it by our molarity. Does that make sense?
Maybe.
So that tells us that we have 0.2975 moles in 425 milliliters of 0.7 molar solution.
Down each of that means each part of that.
Yes, absolutely. Okay. So 0.2975 moles of sodium chloride. We know that that is a number of molecules, right? We have this much salt in a bottle that contains 425 milliliters of this solution that is 0.7 molar. So let's say I have a 0.7 molar solution bottle, okay? And it is 425 milliliters, which is about the size of your hydro flask there, lady. Okay, maybe a little bit smaller. Okay? Now, if I want to know how many moles, how much sodium chloride there is in that bottle of 0.7 molar solution, I have to go through these steps. Do you see how this works? More or less. Okay, let's do another problem. Okay? Let's do another problem. Let's say we have text box. All right. Stretch it out. Okay. We have 6 molar solution of potassium chloride. Okay, 0.6 molar potassium chloride, and we have, no, sorry, it's 6, not 0.6, sorry, 6 molar potassium chloride, and we have 850 milliliters of it. Okay, we have an 850 milliliter sample of potassium chloride aqueous. Oh, did I freeze? Okay. Aqueous, what the? Thanks, lady. I appreciate it. For reals? For reals? For reals? For reals? For reals? What the? Guys. 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 Guys.
Oh my gosh, I fixed it.
I got it. Don't worry, buddy. Got it fixed. Okay. Aqueous solution, potassium chloride, it's 6 molar. We have 850 milliliters of the sample. How many grams? No, let's wait on that one. How many moles of KCl is in our sample? So what are we going to do here? Okay, moles, how many moles of potassium chloride is in this 850 milliliter sample? So, 850 milliliters is not a full liter, but we know that for every liter, we have 6 moles.
Are you bored of this?
No. There is an equation up here that I'll teach you right now. Okay? Couple of equations actually. What? Oh yeah, it's on the wall. Well, we get out of class in 7 minutes.
7 minutes?
Yeah, so we're not gonna have enough time to cover everything about this right now. So I'll teach you the equation next time. But in this case, we do 850 divided by 1,000. Okay? Which gives us 0.850. Right? Okay. Now we multiply that 0.850 times our molarity, which is what? What is the molarity of our solution? 6.85 times 6 equals 5.1. Okay? No, I've got a calculator. 5.1 moles of KCl in 850 milliliters of 6 molar solution. Do you see how that works? So if we had a full liter, of this solution, we would have 6 moles. But we don't have a full liter. We have 850 milliliters, which is 85% of a liter, which gives us 5.1 moles of potassium chloride. Cool?
Yeah.
Okay. Next time, we're going to be doing some problems concerning these ideas. And we will turn them in before Friday. That's the end of this enthralling episode of my YouTube channel. Like and subscribe or whatever.